Hello everyone, my name is Qingyu Zhang, and today I'm going to share this paper with you. The topic is Study on Viscosity Mechanism of Caffeine Crystallization Solutions, and this paper was published by Particularology on 2024. So this is the outline of my today's presentation. I will start from introduction, talking about the classical nucleation theory, CNT, and two-step nucleation, TSN. And in the experimental section, I will show the device diagram. As for the result and discussion part, I will focus on the formation of viscous crystal system of caffeine, caffeine crystal phase interaction, caffeine interact with water, and viscosity mechanism of caffeine crystallization solutions. And my final part is conclusion. In this section, I will briefly introduce two well-known nucleation models. The first is the CNT model, which is interpreted by classical thermodynamics. The thermodynamic driving force for the nucleation is the chemical potential of the solute molecules. When the chemical potential of the crystal is smaller than that of the solution, the system is supersaturated. In a CNT model, a stable nucleus is formed through the sequential bonding of the constituent units. In other words, supersaturation is always necessary for triggering nucleation. However, the opposite is not always true, and sometimes the crystal nuclei are not formed even in a supersaturated state. The region from Cx to Cmin is called the metastable zone. Within this zone, crystal growth occurs, but nucleation does not. Nucleation occurs when the concentration exceeds a relatively high supersaturation level. Supersaturation can often be maintained at this concentration without nucleation for a reasonable observation time. Nucleation is instantaneously initiated when the solution concentration reaches a certain threshold. The width of the metastable zone in a supersaturated solution is closely related to the energy barrier required for triggering nucleation, which is delta G. Namely, the larger the delta G value, the higher the supersaturation degree required for nucleation. And generally, nucleation in highly supersaturated solutions degrades the crystal quality because a high crystal growth rate increases the number of crystal defects. Therefore, the production of high-quality crystals is critically dependent on how quickly the solution enters the metastable zone after nucleation. Another critical point in this CNT model is that the arrangement of the atoms or molecules in clusters formed during the formation of the critical nucleus is the same as that in the crystals formed afterward. The second type is a two-step nucleation model. In this model, two energy barriers must be overcome to trigger nucleation. The first is the energy barrier for the formation of dense droplet upon increasing the solute concentration. The solution concentration increase firstly lead to the formation of liquid-like cluster, followed by dense liquid droplet over the energy barrier. This is very different from the CNT model, in which the molecular ordering in clusters simultaneously increases with the solute concentration. The second is the energy barrier for achieving nucleation from the dense droplet. In this second step, the molecules in the generated dense droplet are rearranged, leading to nucleation of the second energy barrier. The more stable the dense droplet, the higher the energy barrier to nucleation. Consequently, subsequent nucleation is suppressed. In the crystallization process, certain systems exhibit a high viscosity of the crystallization solution, thereby impacting the mass transfer, heat transfer, flow, and separation efficiency. This phenomenon renders the transportation of the liquid difficult and adversely affects its flow and separation performance. The solid particles and liquid resulting from crystallization are evenly distributed rather than stratified. The viscous mixture of solid and liquid forms a viscous system, which impacts downstream production operations, such as filtration, drying, and a smooth progression of continuous chemical industry production. In this work, the target molecule is caffeine. The effect of temperature and supersaturation ratio on the viscosity of caffeine crystallization solutions was investigated. Also, both the interaction among caffeine crystal phases and the weak interaction between caffeine and water were analyzed. In the experimental section, the cooling crystallization method was adopted to carry out batch crystallization experiment of caffeine in a jacketed crystallizer. The experimental device is shown here. A caffeine solution of supersaturation ratio equal to 1.8 was prepared using the following stage. First, caffeine powder was accurately weighed with a certain concentration and completely dissolved at 40 degrees Celsius. Then it was filtered into a crystallizer by a preheated injection filter and gradually cooled to 20 degrees Celsius using a programmed constant temperature water base until the solution achieved a supersaturation ratio equal to 1.8. Okay, so let's move on to the result and discussion part. The formation process of caffeine's viscous crystal system consists of 3 stages. The first stage, at the beginning of nucleation, the caffeine crystals grow poorly through a collision and contact with each other by the fluid, resulting in the primary coalescence of the crystals to form spheroidal aggregates. Second stage, as saturation was consumed and agitation progressed, polymer deformation occurred at the boundary, resulting in a gradual formation of a needle-like crystal cluster. Eventually, the crystals separated from each other when they reach a length and continue to grow into thin, needle-like structures. The third stage, the long needle-like caffeine crystals with high specific surface area re-adhere to each other through the interaction between crystal faces due to their greater frictional forces. Caffeine crystals are crystallized by cooling crystallization, and a solid liquid viscous system is formed with the precipitation of crystals. The effect of temperature and supersaturation ratio on the viscosity of caffeine crystallization solutions was investigated. Among them, the crystallization temperature has a greater influence on the viscosity of the crystallization solution. When the supersaturation ratio remains constant, the viscosity of the solution at 50 degrees Celsius is approximately 10 times higher than the viscosity at 20 degrees Celsius. Crystallization temperature and supersaturation ratio mainly affect the initial concentration, and the higher the initial concentration, the higher the viscosity. Temperature and supersaturation ratio affect the crystallization process of caffeine mainly by changing the pipette staging between the crystal faces of caffeine and the weak interaction between caffeine and water. With increasing temperature and supersaturation ratio, the probability of interaction increases, which in turn lead to greater agglomeration and viscosity of the crystallization solution. Hirschfeld surface analysis is typically employed for the analysis of molecular interactions in crystals. The figure illustrates the molecular interaction, where different colors represent their magnitudes. The red region indicates a stronger interaction than the van der Waals force, while the white region suggests molecules interact at a proximity closer to the van der Waals force. The molecular interaction in the blue region are weaker than the van der Waals force. The fingerprint illustrates that the surface of caffeine anhydride crystal and caffeine monohydrate crystal had the most contact with HH bond. The OH and NH bonds capable of forming hydrogen bonds comprise 34.9% and 41.3% of the interactions, respectively. Meanwhile, the CC and CH bonds, which can form peptide staking, contribute 9.1% and 10.8% respectively. The remaining of interactions are attributed to other interactions. Since caffeine molecules have only two polar carbonyl oxygen atoms and one 5-member nitrogen atom as hydrogen bond receptors, but lack hydrogen bond donors, so hydrogen bonds cannot form between caffeine crystals. Therefore, peptide staking serves as the primary interaction mode between caffeine crystals. Additionally, comparing the interaction ratio reveals that there may be some interaction between caffeine crystals and water molecules. Therefore, when caffeine crystals collide, they come into proximity, which promotes peptide staking and leads to adhesion and agglomeration of the crystals. The growth morphology module is utilized for analyzing crystal habit. As depicted in the figure, the crystal is slender and needle-like, and the length to diameter ratio increases in water. The simulation model closely resembles the crystal habit obtained from the experiment. The simulation results show that there are 6 crystal faces with a significant surface area. However, due to the high symmetry of caffeine crystal faces, 3 primary faces were selected, which showcase the largest crystal face exposure. The result indicates that these 3 crystal faces can form peptide staking because of their exposed purine rings. However, the 3-1-1 crystal face has fewer exposed purine rings and a smaller area, resulting in less effective peptide staking. As a result, the 2-0-0 crystal face and 1-1-0 crystal face were selected as primary crystal planes for the simulation. The simulated interactions among crystal faces depend on the temperature and supersaturation ratio. First, the negative interaction energy suggests an attractive interaction among crystal faces. Furthermore, according to the influence law, as the crystallization temperature and supersaturation ratio increase, so does the absolute value of the interaction energy between crystal faces. It shows that the stronger the mutual attraction dominated by peptide staking. The interaction among crystal surfaces relies primarily on the molecular structure of said surfaces. In a simulation, the chosen crystal faces possess equivalent areas. As the temperature rises, the movement of caffeine molecules intensifies on these surfaces, resulting in an increased probability of intermolecular collision and, subsequently, increased interaction between crystal faces. With an increase in supersaturation ratio, more caffeine molecules are revealed on the crystal surface, leading to increased molecular interactions. This, in turn, causes an increase in the interaction between crystal surfaces. The interaction of caffeine with water in relation to temperature and supersaturation ratio is shown here. The higher the crystallization temperature and supersaturation ratio, the stronger the interaction between caffeine and water. The intermolecular interaction energy indicates that caffeine and water have a strong mutual attraction. At the same supersaturation ratio, increased temperature results in more intense intermolecular movement. This results in enhanced intermolecular contact and more potent interaction. Similarly, at the same temperature, higher supersaturation ratio leads to more molecules having greater contact with each other, ultimately resulting in a more robust interaction. A stronger interaction between caffeine and water makes it more challenging to isolate caffeine crystallization solutions, which result in a thick consistency. The experimental and simulation findings indicate that the interaction of caffeine and water molecules contribute to the viscosity of the crystallization solution. The molecular electrostatic potential provides a glimpse of the interaction active site within a molecule, which provides information about the potential interactions between molecules for the fully optimized molecular electrostatic potential of caffeine and water. When two molecules are in proximity to each other, long-distance electrostatic interactions play a significant role. MEP provides insights into the active sites of molecular interactions, thus offering clues into the nature of potential interactions between molecules. MEP diagrams utilize blue to indicate electron-rich areas and red to indicate electron division regions. Caffeine exhibits positively charged regions near hydrogen atoms, primarily on methyl groups. Electron-rich areas were detected on the 5-member rings of caffeine and on the oxygen atoms present in water. There exists an electrostatic attraction between caffeine and water. Non-covalent intermolecular interactions are characterized using reduced density gradient analysis. Hydrogen bonds are depicted in blue. Green represent van der Waals interactions, and red indicate steric hindrance. The ellipse represents a strong hydrogen bond between caffeine and water. Therefore, water and caffeine molecules form a strong hydrogen bond that is further stabilized by the van der Waals effect and steric hindrance. The results show that the strong hydrogen bond between caffeine and water plays a dominant role, while the van der Waals effect also plays a major role in stabilizing the system, followed by certain steric hindrance. So here is a short summary. The viscosity of caffeine crystallization solutions is primarily due to intermolecular interactions. During the crystallization process, the crystals present in the solution collide and contact each other with agitation. And pipette stacking is generated through the functional groups on the crystal surface, which makes the caffeine crystals attract each other and easily stick together to form partial agglomeration. Simultaneously, the elongated needle-like crystals of caffeine provide a larger specific surface area, which increases the probability of adhesion, resulting in higher viscosity. The viscosity observed in this study is primarily attributed to the interaction between caffeine and water. The analysis shows that the interaction between caffeine and water is mainly dominated by hydrogen bond, assisted by van der Waals and steric hindrance. The solid-liquid mixture formed by caffeine and water is harder to separate with stronger interaction between them. The intermolecular interactions force the caffeine solid-liquid viscous system. So the final part is my conclusion. This paper explains the viscosity mechanism of caffeine crystallization solutions by combining experiments and simulations. The results indicate that the viscosity of caffeine crystallization solutions is mainly determined by the weak intermolecular interaction, such as hydrogen bond, van der Waals force, and steric hindrance. Simultaneously, there is pipette stacking between the long needle-like caffeine crystals, which makes the partial coalescence of the crystals, leading to increased viscosity. And in conclusion, this work has demonstrated that the weak intermolecular interactions cause viscosity in the crystallization solution. And this is the end of my today's presentation. Thank you for listening.